Now we need to learn how to make probability models, which are pretty nice. You have such things as area models, which is kind of what the table is, but we can also call it a table, which they have done right here. What we really like is a tree diagram, which is relatable to what we would consider factoring. So if you guys remember factoring, not that many people do at this point in the year, but if we looked at something like 36, right, we could split this up and say, well, 36 has maybe two factors. 6 times 6, I'm going to use 4 in an old niner, because it doesn't matter, right? And then we can branch this off, making a tree even further, 2 and 2, and then 3 and 3. Then we got our prime factorization, all right? So it kind of looks like a factor tree, just the only difference is right here. It's going to be turned sideways like these. So that's just the way it works. I mean, it's still branched the same way. It's still tree with its branches, but it's going to be moved more sideways so we can keep track of stuff that we're doing as we go. They call those events, but that's really technical, and I don't really care what you call them. All right, stuff that we're doing. This should hopefully make sense soon by the end of the lesson. Okay? One of the other things right here we see is this S stuff right here. So that is what we call set notation. Set notation is quite crucial because set notation is a very classy way of listing outcomes for stuff that we're doing. For any set notation, though, where it's a set of numbers, or values. So we say S, it's a set. The set equals, but this is where it gets real classy. So if you guys mess this up on a test, you could lose points, all right? Especially if you're missing them. What you're going to need is fancy brackets like these. Yes, those are extremely fancy and classy. So if that's what you want to be, you need to master this stuff, all right? So for example, if I took one dice and rolled it, then the set would be 1, 2, 3, 4, 5, or 6. And that would be the whole set. So I need to close the set up by finishing off with another set of fancy brackets. If you're struggling with fancy brackets, here's what you need to do. To get the open set, what you're going to do is draw an S. And then what you're going to do is draw a 2. And that's fancy enough. All right? If you want to close them, what you're going to do is you're going to draw a 2. And then you can draw the S. Bam, fancy brackets.
No.
Probability for each possible event in the sample space. Remember, probabilities always add up to 1. So probability models are a nice way just to organize possible outcomes. Suppose you are going to toss a coin and see how it lands. List the sample space for, we're going to use set notation. That's going to be great. So we're going to list in set notation the possible outcomes of tossing a coin once. So I need a good set of fancy brackets. Oh yeah, so pretty. And what's one possible outcome by tossing a coin? Heads. What's another?
Tails.
What's another?
Tails.
That's it. You're only tossing it once. Okay. So now what we need to do is close the brackets with some fancy brackets, and we feel good because now we feel classy. What is the probability of tossing a heads?
50%.
Yeah, 50%. I can see 1 heads out of 2 possible outcomes. So I'm just going to write the fraction. But fine, I'll write the percent as well. What's the probability of tossing tails? There's 1 tail out of 2 possible outcomes, which is also 50%. Consider the theoretical outcomes for tossing a fair coin 3 times. What is the sample space? Actually, before we do the sample space, it may be good to see what this would look like using a model. Now this one is going to be the tree diagram that I am going to use. And we're tossing this coin 3 times. Alright, I'm going to put this down here at the bottom. And then we'll look at the probability of each of the 8 outcomes, but let's get the model together, which will help us with both of these two questions. Alright, so to start us off, we need to acknowledge that we're tossing this 3 times. So I'm going to list these, starting with toss number 1. And then we'll list the outcomes for these. And then we'll look at what will happen after toss number 1 to give us toss number 2. And then after toss number 2, what could happen on toss number 3. And then we'll list the outcomes. So from this, right here, number 1, I could toss either, perhaps, heads, or maybe I choose to toss tails. You just never know. But it's either one of these, okay? Now that's just from toss number 1. Now remember, this is going to look like a factor tree, right? So, after I toss heads, let's say, I could possibly toss heads or tails like these. Now let's say that I had heads on that second one. Then from that heads, spans out into another branch with heads and tails. And that right here should give us our outcome. So this is just going to trace back, okay? I'm going to look back. I've got heads, heads, and heads. So the outcome is heads, heads, heads. Starting in order from the left heads. So I do the red heads, the purple heads, and then the green heads to give me my outcome right here. Yeah, what about the next one? Well, that would be looking at the branching right here. Another student compared it to the family tree stuff, if you guys have ever seen that. But this is kind of like it, right? You go from tails to heads to this heads. So the outcome for this tails would be heads, heads, and then this tails right here. Alright, so let's go ahead and finish these. If I had tossed tails on the second toss, then I could have resulted in heads and then tails once again, which then would give me a result of heads, tails, heads. But this one would have given me heads, then tails, then tails. Now we're only halfway done though, because I've got to do the other tails as well. Continuing, if I toss tails the first time, then it could branch out and possibly you get heads and then tails right here. From that heads branches out into another set of heads and tails, which would give us these results right here. And then finally, from tails, we could also toss another heads. So now we have all 8 outcomes, which is how many it said it would up here. So what is the sample space for this one right here? Well, the sample space, or the set notation for this. So we do need some nice fancy brackets right here. Now all we're going to do is list all the ones that we have, starting with heads, 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 and I'm just going to go down the list. And then finally, we close this off with another set of fancy brackets. Bam! So what is the probability of each of these outcomes? Well, it would be one outcome out of 8 possible outcomes, which has a decimal of 0.125, or as a percent, 12.5%. Well, there it is. This one wanted us to create the tree diagram, which we have already done right here. All right. Use the list or the tree diagram for 3 coin tosses to fill in the theoretical probability of each of the following events. What is the probability of getting 3 heads? Well, there's only one possibility there out of the 8 that has 3 heads. For 3 tails, it's the same. There's only one out of the 8 that has 3 tails. Right there at the bottom. But what if we had 2 heads and 1 tail in any order, really? Well, two heads, it looks like I've got 1, 2, 3, 3. 3 out of the 8 outcomes have two heads and one tail. And for two tails and one heads, we got 1, 2, 3. So 3 again out of the 8. Alright, we'll use all or part of the tree diagram for these. In fact, we figured some of them out already. The probability of just heads would be 1 out of 2 possibilities. The possibility of heads and then tails, for this one we're only looking at this row right here, and we can see right there that there's 4 possible outcomes. And for heads then tails, only one of them would be heads and tails out of the 4. Yeah, the order here makes a huge difference. We need heads first, which is this one, and then tails, which goes into this branch. That only happens once. So we got 1 out of 4 possible outcomes. Next, we've got probability of heads, tails, heads, which appears to be this one right here. And that is 1 possibility out of 8. Tails, probability of just tails would be 1/2. And then the probability of tails, so starting right here, going into heads. So again, that shows 4 outcomes. Only one of them is tails and heads. And the probability of tails, 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 only 1 out of the 8 right here shows tails, tails, tails. So here are our probabilities for all 6 of these. Alright, as it turns out, most of those that we just did were compound events because we were tossing the coin more than just once, okay? And then we were figuring out the probabilities of each of those. Compound events, finding the probability of these is not too bad if we can figure out what the probability of the actual thing is. For example, if we look back at one of the homework assignments, one of them had like a cycle, perhaps like these. And then it was split into thirds. We'll say that this is split equally into thirds, like these. And then, seems like they gave us some kind of letters from up in count. We'll just make up our own, something like, there we go. Nice. So, just these 3 random letters. We could say, what's the probability of, for example, U in this spinner?
1/3.
Yeah, there's 1 U out of the 3 possibles. What's the probability of getting maybe a T?
1/3.
1/3, right account. Then what is the probability of getting an E? 1/3, right? So here's the way this works with compound probabilities. Is let's say that we started to spin this 3 times. Then maybe we'd want to find the probability of getting U, T, E.
Why you E?
I don't know. It's just random.
What
So,
about ETU?
What
How
about
come it can't be
B,
ETU?
Y,
It
D?
in any case, oh, U, that's nice. It worked out really good.
add a B and a
What about T, U?
So, for this, we have the 3 letters, U, T, and E. What was the probability of spinning a U?
1/3.
It was 1/3, right? What was the probability of spinning a T?
1/3.
1/3. E? 1/3. We can figure out what this probability is simply by multiplying these together. And when we do these, 1 times, this is just fraction multiplication, guys. 1 times 1 times 1 is 1. 3 times 3 times 3 is 27.
57?
Oh man, 27.
Oh, 27.
Well, the calculator will do that. And this would be the actual probability for spinning Ute. We'll be using this method on the next part as well. So this is just a nice quick way to be able to do it. Otherwise you're looking to have to make a tree diagram perhaps. but sometimes that's not convenient either. Fill in the blanks for calculating probabilities for compound events. In other words, for two or more events occurring, suppose we call the first event A, and the second event B, and the third event C. And the probability of A is 50%, and then the second event is also 50%. So the compound probability, the probability of A is 0.5, and the probability of B is 0.5 as well. So we're just going to multiply these together, and that would tell us the probability, in this case 0.25, or 25%. Well, what about the probability of A and B and C? Well, once again, probability of A is 0.5. The probability of B is 0.5. And then finally, the probability of C is also 0.5. So we're just going to multiply these all together, and that would give us the decimal value, 0.125, which is the same as 12.5%. Using words and symbols, state your conjecture for the general rule for calculating probabilities for independent compound events. So we would multiply the probability for each event, and then we would be done. We'll use the rule we found for prior questions to calculate heads, tails, heads, heads, heads. Okay. So let's start this off. We just need to figure out the probabilities of each of these, and then we'll just multiply them. The probability of heads is 1/2. The probability of tails is 1/2. The probability of other heads is 1/2, 1/2, and still 1/2. To figure out this probability, we're just going to multiply these. And the probability of heads, tails, heads, heads, heads is, again, I'm just looking at fraction multiplication radical. But I've got 1 times 1 times 1 times 1 times 1, which is 1. And then we got 2 times 2 times 2 times 2 times 2, which is, so the probability of heads, tails, heads, heads, heads is 1/32. So suppose that you have an unfair coin where the probability of heads is 0.8 or 80%, while the probability of tails is 0.2 or 20%. We're going to compute the following probabilities. Okay. The probability of heads would be something like 0.8 because it's, well, 0.8. The probability of tails is 0.2, which is shown above. So the probability of heads, tails is going to take our 0.8, that's the heads, and we would multiply that by the tails, 0.2, which would tell us the actual probability, 0.16. Now it's going to work the same way for tails, heads, except the order changes. Tails is 0.2, while heads is 0.8, and multiplying these two gives us 0.16, or 16%. It'll work the same way for heads, tails, heads. And we just multiply these all together. So 0.128, that's 12.8%. But then we also want the probability of tails, tails, tails. Tails is 0.2. And we just multiply these, which is 0.008. That'll work. Compare the calculations that you used for the fair coin and the unfair coin. How are the calculations similar and how are they different? Good question. There we go. It's still a heads tails thing, which is kind of the similarity, but now the probabilities are different because one coin is fair while the other are not fair.